Hello, everyone, and welcome to the August 2020 Integration Down Under. We've got our organizing committee, Martin from Perth, Dan from Brisbane, Renee from Sydney, Wagner from Auckland, and myself from Melbourne in end of the second week of 6 weeks of lockdown. Lots of fun. And tonight we have Will speaking about Azure Cosmos DB, lessons learned from the front line. So without any further ado.
Good evening, everyone. Thanks for joining us. My name is Will Velida. I'm a software engineer working for ASB Bank here based in Auckland, New Zealand. I'm also a Microsoft Data Platform MVP, and I'm really excited to share some of the lessons that we've learned using Azure Cosmos DB for around about the past couple of years now. Like I said, I'm a software engineer. I'm a data platform MVP focused on Cosmos DB. I also play around a little bit with machine learning with ML.NET, which is the C# machine learning library, and also spend a bit of my time day to day working with Azure Functions and Event Hubs quite a bit. And I'm originally from the UK, but I've been in Auckland now for almost 10 years, so I like to think I'm somewhat acclimatized as a Kiwi. So tonight what we're going to cover what Azure Cosmos DB is for those who may have a fair idea of it. Usually when I do these things in-person events, I usually ask, has anyone heard of Cosmos DB and what their experiences are, if they have, if they're using it in production, if they're just playing around with it. So if you don't know what it is, we'll cover that very briefly. And then I'm going to go through just a couple of topics that we encountered during our development at ASB Bank working with Cosmos DB, just some topics that we struggled with. I'll cover some theory, maybe go through some anecdotes as well, and just really discuss how you can approach these different topics, because each Cosmos DB is a fantastic PaaS service, but it does come with a little bit of management, a little bit of gotchas here and there, and we'll go through stuff like data modeling, partitioning, throughput, just to hopefully help you guys understand how to approach these things properly when developing with Cosmos DB. And maybe if you've had a little bit of experience with Cosmos DB and struggled a little bit, maybe we can kind of share the pain together through these topics. I'm just looking at Zoom, and I was hoping maybe throughout the presentation, if anyone had any questions, they could pop them in the chat and I could address it then, or I've left some time at the end where we could address it then. So if you have a burning...
For you, Will, I'll watch the chat window and then I can break in if people have some questions. I'll break in and give you the question.
Awesome, thanks. That's, yeah, I usually, again, this type of presentation it would be quite conversational. So cool, thanks for that. Sweet, so let's start with what is Azure Cosmos DB? So Azure Cosmos DB is Microsoft's globally distributed multi-model database service, and it allows us to elastically and independently scale through both throughput and storage to any Azure region worldwide. With Cosmos DB, we can build databases using a variety of different data models. It has 5 different APIs. So if you're working with document data, you can use the SQL or MongoDB API. If you're working with columnar data, there's a Cassandra API for you to use. If you're using key value data, maybe you're using table storage and you need to go global, Cosmos DB provides a table API for you to use. Or maybe you're working with graph data in building graph applications, and you can use the Gremlin API. Cosmos DB provides you with the ability to build highly responsive applications and highly available applications worldwide, and it allows you to bring your data as close to your customers or users wherever they are. Cosmos DB is referred to as a foundational service, so it doesn't matter which Azure region you need to use, you can provision Cosmos DB, which is really, really great. There's guaranteed low latency for both index reads and writes at the 99th percentile all around the world. And there are multiple consistency options to choose from. So there's no trade-off between eventual consistency and strong consistency. There are multiple consistency levels to choose from depending on the needs of your applications. And with a little bit of caveats involved, and we'll talk a little bit about this later, there's automatic indexing on all your items in Cosmos DB, and it's schema agnostic, so you don't need to worry about managing schemas within Cosmos DB. But there are some catches to that, which I'll explain a little bit later. And you might be thinking, well, that sounds great and everything, but what can we actually use Cosmos DB for? Well, here are a couple of examples. We might have IoT applications with telemetry devices all around the world, and we need to have a globally distributed database in order to capture the readings that our IoT devices generate. We might have a gaming application where we'll have users and gamers all around the world, and we need to bring their data as close to them as possible for rapid performance. So essentially, if you need a NoSQL database that's ultra fast, requires minimal management, Cosmos DB is a fantastic database service to use. And just a little bit of an insight on how we use it at ASB without giving away too much IP. Essentially, my team, we follow this event command pattern where we'll have an Azure function, it will generate some events or commands, and we'll process that through event hubs. And some functions will just process the events, but others will persist the events and commands to Cosmos DB following an event sourcing pattern. So with that in place, we're going to go through some topics that I think well, every developer ought to know before working with Cosmos DB, and I'll try and associate some anecdotes with what we encountered at the bank, how we approached different topics, where we failed, where we succeeded, etc. So the one key thing that I think really gets ignored by developers initially because of its schema agnostic nature is data modeling. Now, whenever a new developer will come up to me and says, hey, we're thinking about using Cosmos DB, what's the first piece of advice that you would give to me? And I would say you really need to think about the data you're going to be storing. It's not a relational database, it is NoSQL, and your patterns that you may have followed in the relational world are not going to work out with Cosmos DB. And I'm going to use an example here. Not a banking example, but just a generic example, just to hopefully try and simplify the concept for you. So let's say we have a bookstore, and usually with relational data stores, we would normalize our data and break each entity into discrete components. So for example, we've got a book here that can have an author, books can have many reviews, or authors can write multiple books. And the idea here is that we're actually normalizing our data to avoid storing redundant data. So yeah, for example, if we wanted to retrieve all the books that were written by a particular author, we would have to write a SQL query, essentially get a book for the associated author, along with the ratings and the books that they've written. We need to use elaborate joins to try and denormalize the data and bring that data back whenever we want to see it. And alternatively, if we wanted to update all of this information, that would require us to perform multiple write operations across different tables. And one mistake when it comes to data modeling that developers make is they'll take this traditional approach and think, well, we can just apply that to Cosmos DB. It makes sense to keep discrete entities in separate tables. Cosmos DB doesn't really care about schema agnostic, about schemas, so we can, chop the schema as required, but we can still follow the same approach. But in Cosmos DB, there are a couple of problems to this with having separate tables for discrete entities. Right off the bat, Cosmos DB doesn't support joins across containers. So you won't be able to join data sitting in one container to data sitting in another container. And the way that throughput works, and I'll talk a little bit about throughput a bit later, this does have cost repercussions as well. Depending on how you provision throughput on your databases and collections, having a bunch of different collections for discrete data models might not actually be cost effective in the long run. And finally, if you do need to perform operations across different collections, instead of joining across containers, which you can't do, you might have to basically make multiple trips to your containers or databases and perform in-memory joins, which is a bit messy and a bit untidy. So how do we solve this problem? Well, with Cosmos DB and NoSQL data modeling, we have a few options at our disposal. And at the bank, we have tried to, as best as we can, use some of these practices, and I'll explain as we go along. So essentially, we've got embedding. We can actually embed entities within our documents. We can make reference to data in other documents. Reference data in one document to data in another document. We can also use a bit of both, so we can have documents that use embedding and in referencing. And we can be really, really ambitious. And within a single collection, we can have multiple different document types. And I'll explain how that works in a bit. So let's take a look at embedding. So with embedding, essentially what we're doing here is that we're treating our entities in our model as self-contained items in our documents. So using the book example I referred to earlier, I've got a book here, and essentially what I'm doing is I am embedding our author entity inside our book document. Now, when we're making requests, we're trying to retrieve this data back about this book, we're making a single call. All of our information related to this book is now embedded in a single document. So we don't need, so when we're querying this, we don't require any elaborate joins for multiple collections. It's essentially just one document, one collection, one request. It's a single read operation. Updating it is a single write operation, and then writing a new book is essentially just a single write operation as well. It's really nice and simple. The general advice for embedding: if you can contain relationships between your entities, if you have one to few relationships between your entities, the data that you're embedding changes infrequently, the data that you embed doesn't grow without bounds. So essentially, if you have, say for our book example, if we had an array of authors and that was limited to a certain amount, so let's say 3 was a limit or 4 was a limit, maybe even 5, depending on how many people would actually collaborate on a book. Essentially, if you know that it's not going to grow to say tens or hundreds or thousands, we can actually use embedding. We can embed data within our documents. And if it's queried frequently together, this is where we can all use, if your data follows these guidelines, this is a really good pattern for following embedding. Now, at the bank, we will, without giving away too much IP, essentially we're using a bit of both, but there is a lot of embedding within a main document. So we do follow this pattern a little bit. But let's take a look at referencing now. Now, bear in mind, even though Cosmos DB is a non-relational data store, we will still have relationships in our data that we store inside Cosmos DB. Now, if our relationships are very complex and they're highly connected, it would be better to either stick with your relational data stores or perhaps look at graph data databases. But if we have simple relationships, we can use referencing. Now, if we take our book example again, some authors in our application might publish more books than others. So you might get an author that will publish maybe 2 or 3 books, and then you'll get your serial writers who will publish hundreds and hundreds of books. And it will be impractical to store all the books that they've written within the same authored document. So what you can do is you can add a reference to the books that they've written in another document. And essentially, this is what we refer to as unbounded data. So in other words, our data can grow to an unlimited size. One example from the bank is that we will process batches of payments. And we are very interested in the history of that batch. So our batch will go through several different functions, and they'll go through different status updates. And essentially, we have this like little UI that shows the history of that particular batch. So instead of writing the same full batch document, which is something like 400 lines, which is quite a big document, essentially what we can do is we reference the history and the updates to that batch in another document. And then it's a much smaller document, and we make a call to that history document where we can see the status of that batch. And in this example, we can even avoid having the book array in our author here by adding a reference to the author within our book document. So with referencing, we have a couple of options at our disposal to optimize our data models. And when would we use referencing? So again, if we have that one-to-many relationships, if we have many-to-many relationships, if our related data changes frequently, so essentially in one document, if you're referencing another document and that data is changing quite frequently, that's another use case for using referencing. And also, like I said before, reference data, if that grows without bound, so essentially you could have thousands, maybe even millions of types records of that type of data, that's a way we can, would be another good candidate for using referencing. So that's really some guidelines into data modeling in Cosmos DB. I can't stress how important data modeling actually is, and what we're going to do next is we're going to talk about partitioning, and essentially how partitioning works in Cosmos DB. It's used to scale individual containers in a database to meet the needs of our applications. So every time we persist an item into our containers, essentially what happens is they are divided into something called logical partitions. And this is based on the value of a partition key that we associate with an item that's stored in our containers. Now, every time we add an item to our Cosmos DB container, items within a logical partition they'll all have the same partition key value, and this will be a property within our documents. So for example, if I had a container and I was storing items or storing information related to hotels, and we gave a container a partition key of city name, for example, if we had 20 different city name values within our containers, essentially what would happen is we would have 20 logical partitions created for that container. And these logical partitions will be mapped to something called physical partitions. Essentially, what physical partitions are is they're the internal implementation of the partitioning system in Cosmos DB, and that's managed completely by Cosmos DB itself. So you don't manage the physical partitions, you just manage the logical partitions. And essentially what they are is they're just a fixed amount of reserved back storage and compute. And it's probably best to actually explain this with an example. So in this example, I've got my container containing hotels and it's partitioned by city name. So every time we add a document to our hotel container that has a city name of Auckland, this would be placed inside a logical partition. And let's say we have a bunch of documents, and each time we add a new document with a new value, new logical partitions are created. This will be mapped to a physical partition. Now with this, one or more, as you can see, one or more logical partitions can be mapped to a single physical partition. So here we've got logical partitions for Auckland, London, Redmond, and Paris, and they're all placed inside our physical partition. Now, depending on the size of these logical partitions, we may only require a single physical partition. And remember, we don't manage these physical partitions ourselves. The Cosmos DB team does that for us. But when it comes to physical partitions, there are a couple of things that we need to keep in mind. So the amount of throughput that we provision on each container. Each physical partition can provide a maximum of 10,000 request units. And I'll talk a little bit soon about what request units are. But essentially, when we first started working with Cosmos DB at the bank, and we were trying to persist millions and millions of documents. These were quite large documents, and we were trying to add millions of documents, and we were wondering why it was so slow. And we kept getting errors. We kept getting 49 errors, or too many request errors. So essentially what we did was, our initial idea was, okay, what we'll do is, since we're working in a batch processing type system, when we're getting all these millions of records, will bump up the request units to 1 million and then bring it right back down. And this doesn't actually work due to the limitations on the physical partitions, because essentially what will happen is each physical partition has a maximum of 10,000 RUs, and if you crank it up to 1,000, I'm not sure, quick maths off the top of my head, how many physical partitions will be created, but essentially you have all these redundant physical machines provisioned for you, and then depending on your partition key values, you'll have all your different logical partitions being mapped to different physical partitions, and it essentially, it doesn't work. It doesn't improve the performance at all. It just costs you more money. So if you want to burn your boss's credit card, that's the approach, but you're not going to get fast queries.
We do have one question.
Yep.
How do you do batch insert update in Cosmos?
Batch insert update. So we use .NET at the bank, and we just basically since we're using event sourcing, we're either doing a upsert on the document, which either creates the new document, or it essentially replaces the new document and updates the document in that way, if that answers the question.
I'll wait and see what they come back with.
Okay, cool. Awesome. All right. We're also, for physical partitions, we're also limited by the amount of storage. So each physical partition, I think you can only provision, each physical partition can store up to 50 gigs of data. So if you have more, if you reach that 50 gig limit and you go over that 50 gig limit, another physical partition will be created for you. There's no limit to the amount of physical partitions that our containers can have. As our data grows and the amount of throughput that we provision grows, Cosmos DB will automatically create new partitions by splitting existing ones without affecting the availability of your application. So again, the Cosmos DB team manage this for you, so you don't notice this until, you have no visibility or control over that. But when your physical partitions split, essentially what they guarantee is all the data sitting in a logical partition will remain within that same physical partition. And all that happens with the split with the physical partitions is that the mapping of the logical partitions will change to the new physical ones. So say for this Auckland physical logical partition that I've got here, if that exceeded if that started to grow and started to allocate or needed more storage space on a physical partition, it would be mapped to a new physical partition. And then throughput that is provisioned on a container will be divided evenly amongst our physical partitions. And in terms of partition design, it's important to get this right to prevent something called hot partitioning. So, yeah. So hot partitions occur within our Cosmos DB containers when our partition key doesn't actually distribute the amount of throughput or storage efficiently. And this will result in rate limiting, inefficient use of throughput, and that in turn leads to higher costs. So let's use our hotel container example again before I use a banking example or thing that we encountered at the bank, sorry. Say if we have a bunch of documents that belong to different cities and they look fairly distributed, but then we have lots of documents that have the city name partition value of Paris. It looks like there's a lot of them, and it's almost exceeding the threshold in terms of storage and throughput. This is what we would call a hot partition. Now, if this was our application, we would have to reconsider using city name as our partition key, as it's important that our partition key evenly distributes consumption, distributes throughput, consumption, and storage. At the bank, when we were first working with Cosmos DB, essentially we would have an ID that we would allocate to a batch, and we have batches of different sizes. So we might have some batches with, say, 5,000 payments or 10,000 payments, relatively low. But then we would do tests. We would partition by the ID of a batch, and then we do tests with 150,000 payments or 200,000 payments, and we would discover that when we're querying this data, we would notice a decrease in performance on our other logical partitions due to hot partitioning taking place. So with this in mind, we would need to prevent this with good partition key design. So partition keys have two components, essentially the path and the value. So think of the hotel example from before. We can see that the partition key path is city name. And key paths in Cosmos DB, they accept alphanumeric underscore characters, and you can set partition keys on nested objects within your JSON document. And essentially what it is, it's just a path within your JSON document that you're choosing to partition on. The partition key value would be the value of that property. So in my document, I've got my partition key path of city name, and then the partition key value would be, in this case, Auckland. And this can be string or numeric. It's really simple to select a partition key. Essentially, when you're provisioning your container, you just say, whether you're doing it in the portal or through AZCLI or any other CI/CD tool, you just say, okay, this is what I want my partition key to be. But it's critical to actually get this choice right, because once we've selected a partition key when we create our containers, we can't change it. We had a bit of a nightmare situation during our dev and testing at the bank, where we had all these documents and we noticed that hot partitioning was taking place, and we tried to update and tried to change the container, and we just couldn't do that. So what we had to do is we had to create a new container with the new partition key, and we had to go through the process of migrating the data from the old container to the new one. We use Data Factory, which is fairly simple to set up, but it's still a heck of a process. So my recommendation to anyone who's approaching this is really spend some time thinking about how you're going to partition your data. And good partition keys will have the following properties. So if you have values that don't change, so once you've committed your item with a partition value, we can't update that value. So once you've persisted that to Cosmos DB, so if we persisted that hotel with Auckland in it, we can update that value. So if you have properties within your JSON documents that aren't going to change, that could be a good candidate for your partition key. They should also have a wide range of values to ensure even distribution across your logical partitions in terms of throughput and storage. And this will ensure that your throughput consumption and storage distribution is even across all your physical partitions as well. And it will vary depending on the type of workload that your containers are going to be performing. So with ASB, we'll have some containers that are predominantly used for read-heavy situations. So for this, we may wish to choose a partition key property that appears frequently in queries that we perform on that container. So if you find that you're querying frequently on a certain property, that would probably be a good choice for read-heavy containers as a partition key. Now, for write-heavy containers, we might want to use the ID of the document as our partition key value. The reason for this is that the ID property is guaranteed to exist in every item in Cosmos DB. It has to be unique, and this will help us achieve even distribution in terms of throughput and storage. Now,
Will.
Hello.
We've got one question here too on that migration that you did. What was the approximate volume of data you moved, and how long did it take?
So this was a pretty extreme example. We had 1 million documents in there. And essentially it took us about an hour. And why I say that is essentially the first time we did it, we provisioned, we used Data Factory, and it was just a simple copy activity. So essentially we just picked one container as the source and another as the sink. And what Data Factory does is when it tries to migrate all this data, essentially it does like a bulk insert using a store procedure. And it's a system store procedure that Cosmos DB, that's existing in all Cosmos DB accounts. And we provision that container, I think it's something at 400 request units, the lowest you can go. And that failed a couple of times. We tried bumping it up to 1,000, and eventually it got going again. and I'll talk a little bit about indexing policies in a bit, but we tried excluding almost all the properties, turning indexing off. Essentially, it was just this very clunky maneuvering trying to migrate this data over to the new container. So that was a real extreme example. So about 1 million documents in an hour to answer that question. But that was a really extreme example, and we kind of stumbled our way to get that happening.
Okay, thanks.
Cool. Okay, we can help Cosmos DB optimize our queries by specifying our partition key as a filter. So here in this example, we have our hotel container partitions on city name. By including this property within our queries, essentially what Cosmos DB will do underneath the hood is route this query to the physical partition that this logical partition key value is mapped to. And what's great about this is that if we added additional filters to this query, it would still be routed to this single partition key value of Auckland. So adding additional filters to this query won't change the fact that it will be routed to partition keys, to this logical partition key. So if we partitioned our hotel by, say, star rating property, which is a numeric value, and we wanted to query all our container to return all the hotels with a star rating greater than 4, this query would not be scoped to a single physical partition. Essentially what we're doing is we're trying to scan all our partitions, and this will cause our query to be executed across all partitions, or what's otherwise referred to as a cross-partition query. Now, if we query without using our partition key as a filter, essentially what will happen is the query will fan out to all physical partitions and where it will be run against each partition's index. So each physical partition has its own index. So when we run a cross-partition query on our containers, we're essentially running one query per physical partition. And what Cosmos DB will do, it will aggregate the results across all these different partitions and cause a bottleneck, because what we'll have to do is we'll have to wait for all physical partitions to return the results of the query before the query is done. So you can imagine here we are querying our container to retrieve all the hotels in our hotel container with a star rating less than 4. Our container in this example is still partitioned by city name. So we're performing this cross-partition query. When we execute this query, we're not routing it to a specific partition. We'll have to wait for the query to be finished on all physical partitions before the result is actually returned to us. So you can imagine, say if we have all Auckland documents on one physical partition, and that's 50 gig of data, and we've got all these other hotels on another physical partition, we would have to wait for that query on the Auckland logical partition to finish before we get the entire result back to us, and that will cause a bit of a bottleneck. But having said that, you might be thinking, well, then we should avoid cross-partition queries altogether. But this isn't entirely true. It really does depend. And it is likely in some situations that you'll have to perform cross-partition queries from time to time. We do have a couple of options available to us in order to make it more efficient. I know that the .NET SDK, when you instantiate your client, there is a few options, such as specifying the location of your Cosmos DB account and also your application, that makes cross-partition queries a little bit more efficient. But what you should keep in mind is that you should look to avoid performing cross-partition queries with large containers. Because every time we're checking a physical partition's index, we're charged at minimum 2.5 request units. And I'm going to talk about request units in just a bit, so that will hopefully make more sense in a bit. But depending on how many items you're actually storing within a physical partition, this can get really, really expensive. And we're charged this regardless of whether there are any items within a particular physical partition that fulfills. If there are no items, within that physical partition that fulfill our query's filter criteria. Cool, so we've talked a little bit about data modeling, we've talked a little bit about partitioning, and now This is a real pain point for new developers, making sure that you understand your throughput requirements. This is really, really important, not just in terms of performance, but this is where you start to get charged money. So just to explain, take a step back and explain what request units are. In Cosmos DB, you pay for the throughput that you provision and the storage you consume on an hourly basis. And to ensure that you've got enough, we need to ensure that we've provisioned enough resources, enough throughput on our Cosmos DB containers to perform at all times. When we make operations on Cosmos DB, we use something called request units, and when you look at the documentation, they'll be referred to as RUs for short. And essentially, request units are the currency for throughput. And what it is, it's essentially just this abstraction of system resources, such as memory, CPU, input-output operations per second required to perform operations in our Cosmos DB account. Now, when we provision throughput on Cosmos DB accounts, we provision this in increments of 100 request units, and we can increase or decrease the provision throughput at any time. And depending on the types of operations that we're actually performing on our containers and databases, the amount of request units that we consume will vary, depending on a variety of different factors.
Oh, got one quick question.
Sure.
They're asking for an example of redesigning partition keys when you find that the city name leads to a hot partition.
It is a little painful. So what the Cosmos DB team have done, or that they are working on, it's in the pipeline. Essentially, they've got a partition key designer, and essentially what you do is you can upload your JSON document, and essentially it will suggest a few partition keys for you, depending on, it's like this web tool. You just describe, okay, what kind of workloads does this container gonna it's going to be under, it's going to be under, and it's just generally like a simple advisor which may suggest a partition key property for you. My advice is to really go back and just think about, try if you can at the start, think about the workload requirements on your container, and just think about the workload requirements of your container, and depending on the type of queries, try and keep the partition key property to those properties that appear frequently within your queries. Then it might be that you will have to do some painful data migration, but just to avoid all that, just really spend some time thinking about the design of it.
Okay, thanks.
Cool. So just coming back to throughput, so what really affects our U consumption? So the size of our items, that has a big effect on request unit consumption. So the bigger the item, the more request units that we need to consume to perform read and write operations for that item. Again, indexing. So by default, Cosmos DB will index all our items and index all our properties. We can, within our items, so we can choose to consume, we can consume fewer request units by choosing not to index some of our items. So within each container, essentially you'll have a indexing policy, and you can actually explicitly define which paths in your items you want to include in your indexing or exclude from indexing. Now at the bank, we have these really large really large documents that we're persisting to Cosmos DB. So we use quite a lot of including strategy. So we would just explicitly tell Cosmos DB, this is the path that we want to index on. You can also use composite indexes. So if you're doing a lot of ordering by on multiple different properties within your documents, you can use something called a composite query to just try and decrease the amount of request units that you're spending when you're doing those type of queries. The amount of properties that appear in our items, so the more properties that appear in our items, the cost of performing operations on the items will increase. The consistency level that we set in our Cosmos DB accounts also has a big effect on that. So if you have strong or bounded staleness, which are the two strongest, strong is obviously the strongest, and then the weakest after that is bounded staleness, where you can configure how strong you want your consistency to be. You can consume twice as much request units when performing reads on that compared to other relaxed consistency levels. So the consistency setting on your Cosmos DB account does have an effect on request unit consumption. The complexity of our queries and server-side scripts as well, and how complex they are. So depending on what kind of querying you're using, either using the SDK or stored procedures, that can have an effect on request unit consumption as well. There are a couple of ways that we can provision throughput. So we can either provision it at the database level or the container level. And essentially, when we provision it at the container level, we can guarantee throughput for that container. It will receive the provision throughput on that container all the time. And the benefit of this is that containers that have throughput provision on them, financially backed by service level agreements, provided that you've petitioned your data effectively, the throughput that we provision on a container will be distributed evenly amongst its physical partitions that belong exclusively to that container as well. And if you want guaranteed performance for a particular container, you should should provision throughput, at the container level. We do this a lot in our production environments. So we'll be processing thousands and thousands of payments. The operations can get quite expensive. So we've opted for provisioning throughput at the container level. But you can also provision it at the database level. So essentially, when we provision throughput at the database level, all the containers that will sit underneath that database will share the provision throughput. And it's quite similar to hosting a database on a cluster of machines. Now, since we're sharing the provision throughput amongst all our containers, we can't guarantee performance for a particular container. So say if I have 5 different containers and I've provisioned 5,000 request units at the database level, I can't say that container 1 is going to receive 2,500 request units and the rest of us are just going to share it. They're just all going to share that 5,000 request units specified at the provision, at the database level. So yeah, the portion of throughput that a specific container can receive in this situation will depend on the number of containers, the choice of partition keys for our different containers, and the distribution of workloads across various logical partitions for our containers.
One quick question.
Yep.
I experienced data loss when I used our partition key as a GUID and storing JSON data with session consistency. Is there any reason?
That's a good question. It really depends on. So is this on? Did they say? Does the question specify if it's a write or read? Sorry.
No, they just said I experienced data loss where I used partition key as a GUID and always come back and said write. As
a write. That's a good question. Can I get back to that and think a little bit more about that one?
Yep, not a problem.
Cool, awesome. Okay, so we have a lot. So let's talk about the different ways that we can actually provision throughput. So first up, we can provision throughput at a hard manual level. And this was the de facto choice when provisioning throughput before we could use autoscaling, which I'll talk about in a second. But essentially, when we provision throughput manually, we set a hard upper limit, and then we pay for that upper limit at an hourly rate. And in order to ensure that throughput is provisioned correctly to satisfy our workload demands on our Cosmos DB containers and databases, we'll need to do some capacity planning. And this is where it can get a little bit cumbersome, because at the bank we would experience, when we're trying to persist millions of records to a collection, we would get too many request errors being thrown at us, and we would we were messing around with how much throughput we would need to provision. Because as soon as we tried to consume more request units than we provisioned, we would experience that rate limiting. If we know that our workloads are stable, then provisioning at throughput at a hard manual level is fine. It's a perfectly it's good to, if you have a fair idea of what your workloads are like, then provisioning manually, throughput manually is okay. But for our situation, we have our workloads are somewhat more unpredictable. We have batches of different sizes, so we needed to take another approach. Now, this is where Autoscale.
Does that matter whether it's database or container? So the hard partitioning, does it for the RUs? Does that the manual limit? Is that on the database or on the container or both?
It's both.
Okay.
So you can set that hard limit on both the database and the container level.
Okay.
But we also have auto scaling as well. Now, this is a new feature, a relatively new feature that's been, I think this was at Build when they went generally available with it. We managed to get our hands on the private preview, which was quite good. And essentially what Cosmos DB will do with auto scale is it will automatically scale the throughput based on a workload range that we define. So essentially, we'll just tell Cosmos DB in this situation, you handle the capacity and we'll worry about our workload and worry about our application. So using Autoscale, essentially what we do is we set a maximum throughput level that either our database or our container can scale to. And what will happen is Cosmos will scale between 10% of this at the minimum level and then right up to the maximum level, depending on what kind of operations are being executed against our databases or collections. In this case, billing is still charged on an hourly basis, but what will happen is, in this example, say if you went right up to, here we've got a minimum value of 400 request units and a maximum of 4,000, which is like the minimum you can set for auto scaling. If you scaled right up to 4,000 request units for a minute and then scaled back down to 400, you would be charged for using 4,000 request units just for that hour. If nothing happens in your Cosmos DB account, if there's no operations being performed, you'll just be charged for the 10% of that maximum throughput. And this is really beneficial because before this, if we knew that we were consuming a maximum of 4,000 request units, we would either have to implement auto scaling ourselves by using the SDK, which you can do, or we would just, since we didn't know when batches were coming in or not, it was a little bit unpredictable, we would have to just set it at 4,000 request units at a maximum all the time, which was just a bit of waste of money. Cool, so I've talked about some core concepts in Cosmos DB, and now I'm just going to shift focus a little bit and integrating it with other technologies. So at the bank, we're in the process of developing microservices that generate events and commands, and sometimes we'll persist those those events and commands to Cosmos DB. Now, if you're not too familiar with Azure Functions, and maybe, most of you hopefully are. If not, then I'll just do like a quick refresher on how you can use Cosmos DB with it. Essentially, Cosmos DB, there are some triggers and some bindings that we can use with Azure Functions. So if we want to execute a function whenever a document is created or modified in a collection, we can use a Cosmos DB trigger, which will invoke our function. We might want to do a very, very quick read of our collections based off a SQL query, and we can use an input binding for that. Or we might want to write to our Cosmos DB collections, and for that we'll use an output binding as well. When we first started developing with Azure Functions, we would use bindings quite a lot, particularly, well, we'd use output bindings quite a bit. We would use the trigger binding we would use the Cosmos DB trigger for a couple of couple of functions, and we still do. But there are some limitations to bindings. So currently, as it stands, the bindings only support the SQL API. So there are 5 different APIs to choose from in Cosmos DB. So if you're using a Cosmos DB account that's configured with a different API rather than the SQL API, you would have to use a static client or dependency injection for that. And at the bank, we use both the SQL API, so we were able to get away with using the bindings, but we also use a table API as well, and for that we use dependency injection. Another limitation of the bindings is that essentially what each binding or what each function does with each binding, it instantiates its own client. So essentially, if we have one function that it executes every so often, that's not a big deal. But in our case, we would have a function application with multiple functions inside it. And essentially, each one would have its binding. So it's each trying to instantiate our own client. And this caused a bit of a performance hit for us. And the bindings themselves, still to this date, they use version 2 of the .NET SDK. So the Cosmos DB team released a third version of their .NET SDK, and there have been some, with this release, there's a few improvements in performance and ease of use of the SDK. It's a bit more elegant to use rather than the old document client or version 2 of the .NET SDK was. So if you wanted to use the latest and greatest, bindings, it's not the way to go. But what we found is from version 2 of the Azure Functions runtime, there's now support for dependency injection. So what we would do, or what we're currently doing now, is we'll have a startup file and we'll, sorry, phone's vibrating, not important. Essentially what we'll do is we'll instantiate a static client that all our a singleton, of our clients that all of our functions can share. So rather than having, say, 5 functions within a function application, all instantiating their own clients when they're invoked, they just share a singleton object of that. So if you have got function applications with multiple functions that need to make calls to Cosmos DB, go down the dependency injection route. It is a lot, it's more performant. So let's go into how logging works in Cosmos DB. I'm going to actually talk about logging, going to talk about integrating it inside of vNET, which is something that we do a lot at the bank, and also how backups work as well. So with Cosmos DB, there are a few approaches to logging. So within the Cosmos DB account, you can view at a very high level some basic metrics. So how much throughput you're consuming, how much storage your containers do at a partition level, the availability of your account, your latency, the consistency that's on your account, and then just some simple system metrics as well. We don't use this too much. We use this for just basic diagnostic logging. And then what we'll do is we'll actually dive in a little bit deeper, because you can send diagnostic logs to either Event Hubs, Azure Storage, or Log Analytics. We choose Log Analytics. So essentially we can see who's making requests on our Cosmos DB accounts, how performant our queries are using the query runtime statistics. We can see partition key statistics. So with throughput and storage metrics within the account, what you can do is you can actually see how your partitions are distributed in terms of throughput and storage, and see if any hot partitioning is occurring, and then use the partition key statistics and RU consumption within Log Analytics to actually take a bit of a deeper dive into those metrics. And then you can also look at control plane requests as well. So anyone who's making any changes inside the Cosmos DB portal, you can keep track of that as well using Log Analytics. Backups. Now, backups in Cosmos DB, in my humble opinion, are a little bit cumbersome. Essentially, there are a couple of approaches that you can take with backups. So if you want the Cosmos DB team to manage it, essentially what will happen is, what they do is they'll take automatic backups every 4 hours and then store the latest 2 backups. And essentially, this is, you can't access these backups directly. So what you'll need to do if you have data loss, or if you're losing, if you've deleted a container, essentially what will happen is you call up support saying, hey, this has happened in my Cosmos DB account. Can you please restore it for me? So essentially, if you notice data loss, get on the phone as quick as you can if you want Cosmos DB to handle your backups for you, because they only store the last 2 backups. So you have 8 hours retrospective data available to you. And in the case of deleted containers and databases, these are retained for 30 days. And essentially, these snapshots are stored in an Azure storage account that's within the same region as your Cosmos DB account, so the same write region as your Cosmos DB account. If you have multiple write regions configured on your Cosmos DB account, this storage account, which isn't managed by you, is just provisioned in one of those write regions. But there is coming up point-in-time restores. So this was announced at Build. Essentially, what this will do is it will protect against accidental writes or deletes, and it will enable continuous backups of your Cosmos DB data. And I'm hoping that this will be programmatically accessible, so you can perhaps maybe use a timer trigger to configure continuous backups on your Cosmos DB containers and collection, on your containers and databases. So I don't have a lot of information about point-in-time restores for now, but I'm keeping my eye on this and hoping that this kind of makes it a little bit more manageable and a bit more customizable for our for our requirements. So there are a couple of options that we've done to do our own DIY backup, so to speak, at the bank. Essentially, when we've needed to archive data at a single point of time, we'll use something like Azure Data Factory to do that. But there's also this feature that's enabled on every Cosmos DB account called the change feed. And using those Cosmos DB triggers in Azure Functions, that's a really simple way of getting set up using the change feed in Cosmos DB. So essentially what you can do is you can have a function that will listen to a collection for a configurable amount of time, and essentially any documents that are inserted or updated, and I think there are support for deletes as well, you can listen to changes on those containers, get the document, and then maybe store it in, say, Azure Storage or Azure SQL, and basically archive or persist your data to another data store to back up your data that way. It's not as elegant as you might want it to be, but those are two options to do your own backups if you're required. And finally, just because I work for a bank, we'll talk about integration with vNET. So essentially, how it works with Cosmos DB is you can configure your Cosmos DB account to allow access from a specific subnet of your virtual network. And essentially, this is done by enabling service endpoint, and this will access Cosmos DB on the subnet within the virtual network, and then traffic that from that subnet is sent to Cosmos DB with the identity of the subnet and the virtual network. And once this is enabled, you can actually limit access to that subnet by adding it to your Cosmos DB account. Because by default, an Azure Cosmos DB account is accessible from any source as long as your request is accompanied by a valid authorization token. But once you start adding one or more subnets within vNets, when you're making requests, only requests originating from those subnets will get a valid response. Otherwise, any other requests from any other resource will get that forbidden response. So that wraps up what I wanted to talk about this evening. If you do want to learn a bit more about Cosmos, these resources are pretty good. Gotcosmos.com is developed by the Cosmos DB engineering team, and it provides like a nice high-level architectural overview. There's some great Microsoft Learn courses available for Cosmos DB. The engineering team themselves have developed 2 days worth of content of deep dive labs. So if you are struggling in a particular concept, maybe provisioning throughput or partitioning your data, there are specialized labs for that. So if you need a bit of a deeper dive, I definitely recommend that because it's direct from the engineering team. And they've also got their own dev blog, which is a bit of a recent addition, but it's similar to the .NET blog as well. This is great for upcoming announcements. They're producing a lot of video content now on their YouTube channel, and they'll link it to their dev blog. So if you wanted to keep up to date via their blog, there's that available for you.
We've got
Cool.
one more question.
Cool. Well, it's time for many more questions.
So any tips on diagnosing throttling issues?
So one method that we used at the bank is essentially whenever we perform operations in .NET, we can actually return, as part of their SDK, we can actually see how many request units that specific operation is costing us in terms of request units. So just off the top of my head, in the .NET SDK version v3, I think if you type in, if you're returning a response back, creating a response in Cosmos DB, you can use the it's either request units or resource request units, and to see how many request units you're spending per operation. That's one way of doing it. Those metrics provide like a high level overview as well, to see how many request units that you're actually consuming compared to or attempting to consume compared to your provision throughput. And also you can see how many 429 errors are occurring on those metrics as well. But my main go-to would be to use the SDK and just examine how many request units a single operation is costing, and then just try and multiply that by the amount of operations of that particular operation that you're performing.
And then we had that one other from earlier about experiencing data loss, where I used partition keys as good and storing JSON data with session consistency.
And that was a write operation, wasn't it?
Yes.
That was losing it. I'd be interested to hear a little bit more about that, because I know within a single client session, you're always guaranteed to read your latest writes. So if they performed a write, either there was throttling on it, and I'm pretty sure they would have said that if it was, if that occurred. So either it was, when in our case we use session as well. So if we experience data loss on a write, it's usually that we were throttled when attempting to perform that write. But if the read was performed outside the client session that the write was made, you might experience some eventual consistency on that read. Yeah, that would be my two guesses at it. Otherwise, I'm not too sure what's occurring.
Yep. Okay, and then there's another question on tips on cost optimization techniques in terms of throughput and partitioning.
So cost optimization for throughput, essentially, Autoscale helped us a lot with managing our costs, because it allowed us to be a little bit more configurable. We could just set it at a low rating. With indexing, partitioning, one strategy that we used at the bank is we would set a partition key value for our containers, a property path for our containers, and then we would only index on that partition property. And then we found that when we were querying this document and when we were performing writes, that the amount of request units that we were consuming for each operation was to decrease dramatically compared to just automatically indexing everything.
Okay. That's all the questions we have. Thank you very much, Will. And like I said, the recording will be up not too long after this finishes. So definitely before the weekend. And so if anybody else wants to go back over anything, and then you can always catch up with you on Twitter too. I think you're out there. So, and any other questions before we go? Just one person said, thank you. Great event. So that's good.
Great job, Will.
Yeah, thanks for having me, guys. This was great.
Yep. So thank you very much. And we will say good night to everyone.